Hello, in this video we're going to consider how you can estimate the stationary distribution for a Markov chain that has all recurrent states by sampling the chain. What we will see is that the algorithm for estimating the stationary distribution is similar to the familiar algorithm that you have learned for estimating histograms. There is, however, an important subtlety that we need to remember when we estimate and report the histograms that we extract by sampling a Markov chain. Without further ado then, let's begin by recalling how to estimate a histogram. Let's suppose that we have a random variable that can fall anywhere in the range shown here. To calculate a histogram, we divide up this range into k equally sized segments called bins. If we are generating a discrete random variable, the value can only take particular values on this line. We thus count the number of times each value appears rather than the number of times that the value falls within a bin. To calculate our histogram, we generate random variables and count how many of the random variables we generate fall within each of the bins. This process is shown pictorially here. If we then take the number of random variables in each bin and divide by the total number of random variables that were generated, we can then generate the histogram that's shown as a series of numbers here. To complete this procedure in Python, we would write a program such as the one that's shown here. In this program, yvals is the array that will hold our final estimate of the histogram. As you can see, it is initially set equal to 0 here. We then have a loop that generates all n samples of our random variable here. Furthermore, as we go through the loop, we keep count of the number of times the random variable fell in each of our histogram bins in this line. When the loop finishes, we normalize the histogram by dividing by the number of samples that were generated and finally plot a bar chart showing the distribution. Easy. Now, suppose that we have written the familiar function Markov move that we have seen in previous exercises for sampling from a Markov chain. This function takes two arguments. The first argument is a 2D numpy array that holds the transition matrix, and the second is a scalar that holds the state that we are currently within. This variable sample must be initialized outside of the loop, which I have not done here. Furthermore, to generate the Markov chain, the variable sample must be set equal to the state we have arrived in on completion of the step, so that during the next passage through the loop, we can choose what move to make based on the conditional probabilities of arriving in the other states if we start in the state that we've just arrived at. The key point I want you to recognize here, however, is that other than changing the way that sample is generated, the rest of the code for generating an estimate of the stationary distribution here is the same as the familiar code that we have now repeatedly used for estimating histograms. The only slight complexity is that we have a different method for generating the various random variables which we are using when we compute the histogram. The rest of this code is the same. And in fact, we can hide this complexity by simply changing the function that is called to generate our sequence of random variables. Critically, however, generating an estimate of the stationary distribution for the Markov chain is not difficult. It is simply a matter of using what you already know about estimating histograms. As I outlined at the start, however, there is a subtlety that needs to be remembered when we estimate the stationary distribution for a Markov chain. This subtlety is related to the way that we calculate the errors on our estimate of the probability mass function. As I have argued repeatedly during this course, estimating these errors is essential. If we have not provided an estimate of the error in our results, then those results cannot be reproduced by other research groups. Consequently, if there are no errors in our data, we are just reporting random data and claiming it is meaningful when it is not. In previous exercises, we have seen that you can calculate the errors on the estimate of a histogram by using a code like the one shown here. The key line that calculates the width of the error bar is this one. In computing the errors in this way, we are assuming that the following quantity is an estimator for the variance of the random variable that has been sampled. In this expression, n is the number of samples that were generated, and x bar is the mean value of the random variable. I should note that this expression is a version of the expression in terms of the sum of squares of the random variables and the sum of them and the square of the mean that we would normally write for the estimator of the variance. We can use this expression here as all the random variables we have averaged are Bernoulli random variables. This expression is simpler and it drops out naturally if you assume all your random variables are either 0 or 1, as they would be here. The critical thing to recognize here is that this is not the variance that we need in order to provide our errors. We need the variance of the mean of a series of random variables that have this variance. In previous exercises, and in the code shown here, this variance, the variance of the mean, would have been calculated using this expression. This expression assumes, however, that our random variables are all independent. This is the kicker, though. This expression is only valid if the random variables that we've added together are all independent. We have sampled a Markov chain, though, so we know that the list of random variables that we have generated are not independent. We thus cannot use this expression to calculate an estimate of the variance of the mean. If we do use it, we will underestimate this variance of the mean, as we will not have taken the correlations between our random variables into account. Thankfully, we have learned other ways for calculating an estimate of the errors. In particular, we have seen how we can write code like the one shown here. This code generates multiple estimates of the histogram. The mean is then obtained by examining this distribution of these random quantities. In previous exercises, we have not liked to use this method as it is more computationally expensive. If we are estimating the stationary distribution for a Markov chain using an algorithm like this is essential, and it is the only way to properly account for the correlations. We have to bite the bullet and accept the computational expense in this case. We can't simply use what we know about the central limit theorem, as we don't have a good estimator for the variance of the mean. I hope that is reasonably clear. Thanks for your attention, and as always, good luck with the exercises.